Yeah. So we can start.
Thank you. So I will describe some more than we have been doing with the projective space. So it's joint work with Felix, Matthias, and David. So maybe I should state the results. So one result will be that the automorphism group of this is the and this is the quotient of GNN plus 1 of R, so invertible matrix by diagonal matrix invertible. And so we started to work actually last year. We discussed this in the previous meeting that was there, and it was not at the time. It was not clear at all that it was actually analysis. That's so maybe and Pn is defined as so it's a scheme. So it's a set with a property. So actually this is the same as automorphism bijection of sets. And in univalent theory, it's the same as this, where the equality is in U as a type. So it's okay. And so why I was interested in this? It's because this group is actually the same as automorphism. So that I will first will start with the motivation. Why I wanted to look at this. So it's the same as this group, but no, it's automorphism of R algebra, not bijection of sets, so as R algebra. And this holds for and constructively, and for any local ring, you have, if you look at the automorphism of this R algebra, you have this. So this corresponds to more generally, so you have, so this is known, it's a reformulation for local ring of something called the Scholen-Noether. I mean, easy case of Scholen-Noether theorem. So the automorphism of the central simple algebra are central, and this is so automorphism of this is given by a matrix. And then it's central, so the thing that commutes with everything are exactly the diagonal matrix. That's why you quotient. Okay. And why it's interesting? It's so this is connected to the previous talk. It's so it's to define. So whenever you have this, that means that you have two. You will get two possible delooping of this group. So one delooping will be the set of X in X and the other delooping will be the set of R algebra that are merely equal to M and plus 1. And when you have two delooping, and this will all be any, not only in the Zariski corpus, but in any corpus, you can work with this LPPL topology, and you will get, so there's two types, they are both delooping of these things. If you know that Pn is LPPL, so that's where what Hugo presented is essential. So if you know that Pn is LPPL, this is still, this will be a delooping of this. This is a delooping of this. And so you have a uniqueness of delooping in theory. So that means you have a good correspondence between this. So that means whenever you have a problem about something here, you can translate it to a problem to a matrix. And that was so a scheme satisfying this. So the scheme X which satisfies this is called Severi Brouwer. by ET. Okay, actually, the notion of torsor was introduced to study this and to translate the problem of the schemes to a problem of matrices. And then we have access to this because of this correspondence. So that's that plan. This is, and he was doing it with our field, and hopefully we can do it in the synthetic setting. So, so that was yeah. So that's motivation for looking. One motivation for looking at this.
I have one question. So I think I missed why is FPPF important in our?
I mean, it can be done. I mean,
okay, yes.
So any topology, so just you know that this is yeah, in this local this topology. Okay. Yeah, and so this thing about PN equal PN, also it's unexpected results because it says so any bijection of this has to be given by an element here. So which means that automorphism of PN, I mean they preserve a lot of structures. For example, they will preserve collinearity and this, which is unexpected. And the situation is not at all the same for if you look at Rn, I mean An equal An, so A2 equal A2. For instance, there's it's much more complicated. So there is this nice example in Wikipedia, so you can define this. So this defines an automorphism of the plane. So automorphism of the planes are very complex, but in PN, it's a miracle. It becomes a simple description, so it's a very rigid situation. So that was okay, and so the argument I will present. So it should follow from the three axioms, type theory with this three axioms. And more generally, so we will describe the Picard group of PN. Okay. And what is this? So it's where GM is another notation for first. I mean, multiplicative group, unit of so, and also a classical result of our field is that so this is Z. Okay, and we will prove this. I mean, we will prove this, and description of automorphism will be a corollary. But actually, more generally, so we will use this to describe more generally the function of this set to this set are the one that we expect. So what are these functions? They are given by so m plus 1 polynomial, homogeneous polynomial. So, and that's also yeah. So that's also nice. This is rigid like this, and it's not easy. If you look at this as a functor of points, it's not easy to see this. That are the natural transformations. And so, what's interesting about the story is and it was so mainly so it was Matthias who noticed this is that actually so this is defined as a so set prolongation of PN BGM. And Matthias noticed that actually it's good to describe these types directly. And we have so we have a more refined version of this equality. It is Z. It's actually we have a description of this space. And this will be so it will be a canonical, I mean a map of Z times VGN. This will be an equivalence. And so it's interesting, even for the proof, it's actually interesting to work at this level of types and not only here. Okay. So also, what we use is this other description of Pn that has a set of so line bundle line with Tn of V. I use so there, so I recall that so DGL can be, and it's another application of this. I mean, uniqueness of the looping. So we have another way to describe BGM. I mean, we have a direct way of describing BGM as a set of R-module that are merely equal to. And so, which means that there is a lot of maps, natural map from Pn to BGM. Okay, so the projection is if we have an element of BGM and we project. So that's a natural map, and more generally, so we can take if D is an integer, we can take so we have an inverse, so the dual of D. I don't remember what yeah. I don't remember the notation, but was dual. So there is an inverse and there is for the tensor product, and then we can define a tensor product of V times. That's, we have V minus 1. And so in this way, we have a line bundle of Pn that are familiar line bundle of Pn indexed by Z. And I don't remember if it is OD or O minus D. But that's
minus is also the sub bundle and plus so plus one is the quotient bundle.
So that should be minus.
So I mean, so if yeah.
Oh, minus. Okay, and so the goal is to prove that there are all the line bundles. Okay. So I will not I will go into the detail. I will do a high-level version of the proof, but I wanted to first to state some result. I mean, with this Tn of V. So that's how we found quite amusing. So if we can look at the so we have this family of space Tn of V, So we can look at what are the maps. It's not directly related, but yeah, it's nice to observe this. So we can describe actually what is this this thing, and so this is actually yeah, first of all, this one. So we can ask what is this, and this is actually G L plus 1. So why is it so? It's because
maybe you mean that the one inside is GLN plus 1 of V?
Sorry? No, I mean this.
Oh. Okay.
Yeah. So I mean, and the key is that so what we have is a family of sets over a BG of something. So, and the general result is that whenever you have a family, when you have such a family, I mean, what is this product? It's a fixed point of so it's actually the map. So you can look at the value of this on the special case of R1. This. And so this, the general result of this type is actually the set of elements there that are fixed points by the GL action.
Okay.
The same as the multiples of the identity are central in the matrices. I mean, you choose a trivialization of B, and then you write down this map.
Yeah.
And well, and then it does not depend on the trivialization because it's the same on both sides.
So maybe I can reformulate this. I mean, general result in fact whenever you have whenever you have such a family, so it's the same as X star with G action. So to give a set with a G action is the same as to give a family of set over BG, and the result is that the product. So it's completely general. Product of this family. Of X is actually 6 times. It's a completely general result of the univalent activity. So we instantiate this result to this special case. So now we have to compute the fixed point. So what is this that we have to compute? So first we have R1 plus 1 is minus 0 to R1 plus 1 equals 0. So we can look at these maps, and so this is instead the plan. And then also a lemma that we can be proven is that actually this set is so there is restriction map for this set to this set, and this is an equivalence. Set. So we look at points that are here, and what are these points? So there are points that send n plus 1 vector to n plus 1 vector. Alpha like this, and it should be invariant under the GM action. So what does it mean? It means that this map should satisfy alpha under x equals under x over GM. But any such map is a polynomial in the setting of in the synthetic algebraic geometry, and a polynomial which satisfies this is a polynomial of degree 1. So this, and then also it should say, so that's a map alpha, but we have also the condition that x is different from 0 implies x is different from 0. Okay, and from this we deduce actually alpha is in the so alpha in GM it should be invertible. Yes, invertible matrix. That's very good. Okay, so that was this, and so it shows that yeah, I mean this will be the main idea why we will get PGL, that we have this situation. Okay. So and more generally, so if we have so similar results, I will only state not prove. We look at so one so B, say like this. So by similar computations, you see that it is the same as homogeneous polynomial of degree B. And if we have no, wait, that's nice. Yeah. Okay. So yeah, so it's example of computation with higher types. No, so the proof of so now how do we compute this? And so the argument will be to show that if we have a line bundle on Pn, it's actually a trivial on each chart. That's, that will be the idea. I mean, here you have Pn is covered by n plus 1 chart. An element of Pn is like this, and the chart. So it has to be trivial on each chart. And the problem is that if we were overfilled, then that will be easier. So because then we can show directly actually that a line bundle. So a line bundle over yeah, overfilled. I mean it's a simple, relatively simple result. Because essentially it's because the K a polynomial ring over a field is a GCD domain, and over a GCD domain, so any line model is true. But the problem is that R of X is not R of X from Xn is not a GCD domain, so you cannot do this. So that's but I mean, it has been done. It's a classical problem in algebra that is well studied actually, and the problem was, can we follow what has been done in the synthetic setting? So the plan is to start to first look at this line bundle on P1, and use this case, and then we generalize. And so a line bundle on C1, so the lemma, which is called the Aurochs lemma. So if you have a line bundle on P1, so if you restrict it to the chart, so N restricted to the, so it's covered by bluing A1, so restrictors on finance. So the two line chart is triggered. So the restriction of N is triggered with that chart. And that was the Aurochs theorem. And and this was proved, so it's an old result in 1963. And but the proof is very, I mean, with the proof that he had, it's not clear. I mean, it's an external proof, it's not clear at all. We can adapt it to synthetic, in the synthetic setting. But this result was used, generalized later. So the famous paper of Quillen, where he generalized this. And in his paper, so he proved what is known as Serre's conjecture, that any projective module, but not necessarily a Frank norm, over a polynomial ring is trivial. So that was known as Serre's conjecture, and he has, so he proved this, and for this, it needed a generalization of Aurochs theorem, and the generalization is replacing 1 by n. But he proved a more general result, so it's not about a line bundle, but it's about projective module, so finite forms. But interestingly, so his idea was to start from case 1 and generalize it on n. And for this, he introduced a technique which is known as Quillen patching. And when he produced this paper, so people looked at this again, and then a lot of actually elementary proof of Aurochs theorem were found. There was so the original proof was very classical, but then people discovered at least 3 different proofs of Aurochs theorem that can be done in the synthetic setting. So that's so actually, so this part so is valid, can be done synthetically, and it's an algebraic, so it's an exercise. Start from a proof of Aurochs theorem and you translate it to a constructive proof. And so there is a proof of this in Lombard-Equité, in the book of Lombard-Equité on constructive algebra. And in our draft, so we do another proof of this result. But I think all the proofs that exist can be translated. So the case 1 is can be done algebraically. So now the problem is the generalization from 1 to n. And what is interesting is that so using Matthias' remark, we don't need to follow the technique of Quillen patching. So we will use so we will use this direct description of this type to go from 1 to n. But before, so I should say, so once you have this, so once you have the power theorem, okay. So then so you take a line bundle, you want to study it, and then you know that it's trivial on each affine chart. So what you have actually is what? So you have a glued pair of x with itself. Okay. And so the problem reduces to, once you have this, the problem reduces to compute invertible element in this. Invertible element. In this way. And so this is because to give the line bundle will be exactly given by an because you have to glue this line bundle, the trivial line bundle over this to this one. And this is also something, but it's much easier than Orok's theorem. I mean, it's simple to compute invertible elements here. So what's the results? So using that R is local, but it will work more generally if R has no non-trivial idempotents. You can see that an invertible here is exactly. So you have x to the d, where d is in z. And then you have a negative part. So 1 plus n minus 1, x minus 1. And then you have a positive part. So 1 plus 0 plus n1 plus 1. Next. And so any invertible element can be written uniquely in this form. Okay, so d is in z, and c minus 1, L0, A1 are all nilpotents. And so, and using this, then you can show that a line bundle actually has to be, on P1 has to be of this form. Once you have this result, sorry. So, and what does that mean? Another formulation of this is actually, so you get, you have this map on so if you have a line bundle 0, D, we associate the map that X is so V0 minus. So a reformulation of this is that this map, but now it's a map between the groupoid. So the map like this is surjective. So any element here is merely equal to one of this element. And I mean, and then the remark of Matthias was that actually this map is if you look at the map, looping map of loop space, it's actually an isomorphism. That's so in loop space, you get GM into one GM. And then, yeah, so I will not go to this one loop makes this isomorphism. And then we can use the results in the whole book, but hence this map is an equivalence. And this is a result because it's we have a better descriptions if we don't compare P1 or PGN. So this result actually should be connected to so nice exercises. This, okay, this equivalence, and this is V of Z. And curiously, so you have the same situation for BGM. So actually, the BGM times Z is also equivalent to BGM. And this is because if you look at so automorphism of group from GM to GM, I mean, one can mean the setting of synthetic algebraic geometry. This is itself. So you have something similar. So actually, so BGM to BGM, it's the same as P1 to BGM, but we were not able to use this to simplify this proof. It looks like we need. The core of the argument is very this algebra. This lemma algebra. It's fine. Okay. Okay, so now I will give the high-level description of what happens next. So once we know this, then using this, we can show that is trivial from which and so I will not reproduce the proof, but so it's as I said. So what's interesting is that we don't need to follow Willem matching argument of one to one, but we can use this. So instead, I want to so to show how to use this. So once we know this, and so we have a trivial on each function, and then we need to describe what it means to patch together this trivial line bundle in a function, and it's a description of what are the invertible elements, something like that. So it's a technical lemma, but which is feasible. So corollary for this. So we get the same thing as before. So BG, yeah, BG adjacent. Yeah. So this description of the PN. And actually, Matthias has a direct proof of this for N. So Matthias is an alternative of this fact, geometric proof of this without going through the open chart. That's this one. So now I want to describe. Yes, so if I want to know how to use this to compute automorphism of PN, and also how to compute PN or PN. Okay. So what is PN or PN? So it's PN sigma d ETM. So I will not so the proof. I mean the proof that it is. So that's R module exists with the TM module. And now we use so now we use the side theory. So a map like this, it's actually given by a map from PN to PN. With all this. So with a map from PN to
TM of L of X.
Thank you. And but we have this equivalence. Okay, so we can simplify this part. So we can instead of having this sigma of this type, we have a sigma of BGM. Yes. Something. So that's V0 and V. And for all x is N. So TM of so O V0 cancel. Okay, and then we can use that this is also Pn is also sigma V T and V. Okay, so we can replace this Pn by the sigma times. And then, so what we get in this way is sigma V0 and VN, sigma V in both for all V in VN, Tn V into Tn of V. So easy way. Okay. So that's the computation. And by and then we can use the same, so it will be a set of fixed points. So we get, in this way, we get the map from Pn to Pn by using a similar reasoning as the one I mean with so product over the B or something is a fixed point. We get what we wanted. So a map from Pn to Pn is given by m plus 1. So m plus 1 homogeneous polynomial. But we have to be, I mean, there is this part here, which means we have a quotient. So, I mean, we have a quotient by what we expect to characterize this map. So it was nice. And then, so once we know this map, so, I mean, a similar reasoning, what we wanted, so n plus 1. And I so wanted to finish by yes, a nice application of cohomology groups. This that was due to so Berlin at this point. So what we expect from this is that so if n is strictly bigger than n, if n is bigger than n, the map is constant. And this is so application of cohomology and the fact that we can compute the cohomology of Pn using change cohomology. So we can compute actually. So we know that Hn of Pn is equal to 0. And we know that it is, yeah, we know this. So, no, this map is given by this map, which is, we know it's given by polynomial like this. And so we can define the, I mean, they are defined to proportionality, but the predicate, so we can define ui open, x belongs to ui, meaning that ui is invertible. This is an open subset of Pn, and it's a nice exercise actually in Archon that there's so affine like this, open like this, they are affine. And it's elementary exercise. We can do it synthetically. So it's an affine open. And so affine open Pn. And each intersection, so each intersection is then Z will be also affine. Hence, acyclic. So that this means we have, if we have this situation, I mean, we get a covering, if it's not constant, so we get a covering of Pn by m plus 1 acyclic, so covering. M plus 1. Like this. And this contradicts this fact. this proposition as an application that we can compute the cohomology of projective space. Yep, and I think yes, that's what we put it.
So I have a very basic question. I think I didn't understand your lemma about the units in R x 1 over x. So the units without it, so the units that are in R,
yep,
they seem to be those that are just like 1 plus some real tokens.
No, so that's wait a minute. I forgot. No, sorry, I forgot. You're right. So where is the statement? So yes, in the statement, good point.
Yeah, but now say if 2 is invertible. And
yeah. Indeed.
Okay.
Yeah.
Then the question is really basic.
Yeah, it's not. It's yeah, perfect.
Okay.
Yeah. Sorry for this. Yes. It's very funny. So that was what I should have written. So that's a unique instances where U is the
okay, so what about the
so units
and what did you say was the degree of this on the blackboard above? How much is put on the degree D?
Yeah.
So we can still choose the degree.
Yeah, but of course the degree is negative. Not,
yeah, but what happens now if we say if I just multiply everything by just x0, then I increase the degree of the polynomial, but it looks like something which is not everywhere defined. But when on x0 equals 0.
I mean, we need, so it's given by this, does satisfy the effects, I mean, it should satisfy this condition.
Okay.
So it's given by this, and that's when you satisfy the condition. So the statement is correct, but if you want, conversely, if you give me n plus 1 polynomial, I want to build a map, I should satisfy this.
Yeah, okay.
Otherwise, it's not.
Got it.
Thanks. Yes, and also, as I said, so you can have different, of course, I mean, polynomials that are which is up to the proportionality. So you can have different polynomials that will define the same. You need to cut out. So you have a projection of this set of homogeneous polynomials that explain these conditions. And so for automorphism, what happens is the polynomial needs to be of degree 1, and then this condition will be force this polynomial to correspond to an invertible matrix.
You said, so how do we get degree 1? And equals because we have an automorphism here.
Yes, it's I find it a nice, I mean, use of higher types. to be able to manipulate those types of random sets.
Could you elaborate on this last step on the upper right blackboard where you apply this fixed point formula because it's not directly involved, it's not T and V, right? So that's exactly the formula.
Oh, yeah, right, yes. So it's but sorry, so it will be this part will be the same as before. So we will get yes. So, so we have to compute this. So, I mean, so we can, so this will be 7 this. This is good. So that it sends something different from 0 to something different from 0. And then, so we need to compute fixed point of this. So when we apply this to R, so so first, so I want to say that if I have an element here, it's actually given by polynomial. So let's see. So actually, so if I want only an existence, I mean, the idea will be that this V0 will be. You can assume that it. Oh, yes, sorry.
Can you just do it the other way? You want the set of orbits for the GM action.
Yep.
And then, okay, what is the orbit type? It's well, the thing we computed before. And that's the right way to think about it.
Yeah. Yeah. Good. I mean, yeah, but the point, I mean, the point was saying that you, as you said, you have this, which is a set of orbits related to Cauchy's. Yeah. Yeah, that's a good question. So, yeah. Matthias also told me that we need to expand on this. Yeah. Yeah, so you get polynomial, and then as before, so you need, since you need to remember that it's different from 0, it's different from 0, else you need to put these conditions. So, yeah.
Yes, so thank you again, Thierry.